All right, let's dive right into this explainer. Today, we're unpacking the actual machinery behind large language models. Even if you follow AI super closely, taking a peek under the hood at how text generation actually works is just completely fascinating. So let's unpack the source material and figure out how this incredible architecture comes together.
It really all begins with one core question, right? How does AI actually generate text? Well, it turns out this massive, world changing technology is essentially just a superpowered version of the autocomplete on your smartphone. I know, it sounds crazy, but to see how we get from guessing the next word in a text message to writing complex computer code, we need to break it down.
So here is our roadmap for today. We're going to hit the building blocks of language, the problem with context, the transformer architecture, how we train these giant models, and finally, taming and customizing them.
Starting with section 1, the building blocks of language.
Okay, so you and I read words, but AI, it doesn't. It uses what's called a token, which is literally the atomic unit of language modeling. Now, a token can be a whole word, a subword, or even just a single character. For example, the word cats is actually processed as two entirely distinct chunks. You've got the root, cat, and the suffix s. As a general rule of thumb for English, one token works out to be about 3/4 of a word. Basically, everything the AI ever processes is chopped up into these tiny little puzzle pieces. So what does it actually do with all these tokens? Well, quote, a language model estimates the probability of a token or sequence of tokens occurring within a longer sequence of tokens, end quote. That pretty much sums up the entire field. Translating that into plain English, all these models are doing is calculating the statistical odds of what comes next. They look at the tokens you gave them, crunch the numbers, and figure out the most logical next token. It's really just a giant game of probabilities.
Think about a model trying to fill in the blank at the end of a sentence. It literally generates a probability table. Cook soup might sit at the top with a 9.4% chance, while relax is way down at 2.2%. Text generation is just reading those probabilities and picking a winner, over and over and over again. It is, quite literally, a mathematical game of fill in the blanks.
Moving to section 2, the problem with context. For an AI, context is notoriously hard. Imagine the phrase, orange is. Well, what comes next? Is it ripe because we're talking about the fruit? Or is it cheerful because we're talking about the color? Older language models, which use something called engrams, they'd really only look at the two immediately preceding words to make a guess. And if the AI only sees orange is, it just fundamentally lacks the context to make a smart prediction. It's essentially flying blind. Which brings us to a massive turning point in the technology. Early models, like those engrams and recurrent neural networks, they read sequentially, token by token. That created a very limited memory window. Basically, the further back the context was, the more likely the AI was to just forget it completely. But then, transformers came along and totally changed the game. Why? Because they evaluate the entire context all at once, instead of just reading in a straight line. Which perfectly sets up section 3. Enter the transformer architecture. Now, transformers are these enormous neural networks with billions of parameters, but their core function breaks down into two surprisingly simple steps. First, an encoder takes your input text and converts it into this deep, mathematical intermediate representation. Then, the decoder takes that representation and converts it into the final output text. Think of it like language translation. The encoder reads English and turns it into a pure mathematical concept, and then the decoder takes that abstract concept and writes it out in French. But how on earth does a transformer understand all that context so well? The secret sauce, the real magic here, is a breakthrough called self-attention. Self-attention is a mechanism that looks at the whole sequence and asks, on behalf of every single token, hey, how much does every other token here actually matter to me? It actively weighs the relationships between all the words simultaneously. Let's see self-attention in action. Take the sentence, the animal didn't cross the street because it was too tired. Now, as humans, we instantly know it refers to the animal, right? Through self-attention, the AI model is drawing these invisible mathematical connection lines between it and all the other words, and it ends up scoring animal with a much, much higher relevance than street. And the crazy part? The models don't just do this once. They use multi-head, multi-layer self-attention. They stack these attention layers on top of each other. The first layer might just figure out basic grammar. The next layer figures out who is doing what to whom. And by the time you get down into the deep layers, the model is grasping highly abstract concepts like sentiment, tone, and complex thematic links. That right there is how it builds true understanding. All right, section 4, training the giant models. So, how do we actually teach these things? The primary method is a colossal game of fill in the blanks, technically known as masked predictions. We feed the model billions of sentences from the internet, but we intentionally hide or mask certain tokens. The model has to guess the missing piece. And at first, it's terrible at it. But every single time it guesses wrong, a process called backpropagation reaches in and tweaks the model's internal math just a tiny bit so it guesses better the next time.
The absolutely crucial point here is that through enough of this masked prediction training, the model graduates from just guessing single words to generating entire sequences. This brings us right back to our superpowered autocomplete analogy. Once fully trained, a massive transformer can calculate the probabilities for whole sentences or paragraphs at once, mathematically choosing the sequence that makes the most sense based on everything it absorbed during training.
And finally, Section 5. Taming and customizing LLMs. Let's talk about how we take these raw, giant foundation models and actually make them useful. First up is fine-tuning. This is when we give the model a little bit of extra training on a very specific data set. Like if you want an AI medical assistant, you'd fine-tune it on medical records. It keeps its original massive size, but its predictions become hyper-focused and way more accurate for your specific use case. Next is distillation. Giant models are frankly incredibly expensive to run. So distillation is this clever trick where we use a massive, computationally heavy teacher model to generate a bunch of perfect examples. Then we use those examples to train a much smaller, faster student model. The student essentially learns the specific task from the teacher, which saves immense computational cost while keeping the actual response times lightning fast. But hey, what if you don't want to change the model's internal code at all? Well, that's prompt engineering. You can drastically change how a model behaves just by tweaking how you ask the question. There's zero shot where you just ask directly, or you can use one shot or few shot prompting, giving the AI one or several examples right in your text prompt. By giving the AI a pattern to follow, it just matches that pattern in its answer. No extra training required whatsoever. And for tasks that are just way too big for real-time generation, engineers use offline inference. For example, when Google Search needed to translate hundreds of COVID vaccine synonyms into 50 different languages, they definitely didn't do it live every time someone typed a search. They ran the giant model offline, gathered all the predictions, and just cached the answers for later. It's a remarkably brilliant way to use a massive model efficiently. Now, we have to be clear, no technology is perfect, and understanding these limitations is absolutely crucial. Large language models frequently suffer from hallucinations, meaning they will confidently state things that are completely, totally wrong. They also come with an incredibly high compute cost, burning through massive amounts of electricity. And very importantly, they suffer from bias. Because they're trained on huge chunks of internet data, they inherently absorb and reflect the biases present in that data. It's a necessary reality check. These tools are powerful, but they require highly responsible use. Which leaves us with this final, genuinely provocative question. We know that right now, making a transformer larger almost always makes it better. But as these models consume ever more massive amounts of electricity, data, and silicon just to understand broader contexts, is there a physical or practical limit to how large they can get? Have we found the ultimate architecture, or is the next major leap in AI waiting just around the corner? I really hope this explainer has given you the foundational knowledge to follow that debate as it unfolds. Thanks so much for exploring this with me, and keep learning.